So, good afternoon, everyone. Welcome to week 5 of the live sessions on design of steel structures. I am your TA Danish Bashir from Structural Engineering Division, Department of Civil Engineering, IIT Madras. So, in last couple of the weeks, we started from the basics of the design of steel structures, wherein we see the calculation of the loads. Then we saw the basic connections like butt joints, riveted joints, and butt joint, lap joint. Then we saw different fasteners like rivets, bolts, and how to design the riveted connection and bolted connection, both in lap joint as well as butt joint. All these things were discovered in previous weeks. Then we moved to some other advanced topics like welds design welds where in last class I taught you what we mean by different types of welds like fillet weld and butt weld. What are their specifications, what are their symbols, and how we represent them actually. And today in today's class we will be continuing on the same topic from where we left in last class. So I hope all of you are connected with me. So I shall begin today's class with the design of the butt welds. So before I begin into the design of the butt welds, there are some technical terms that we need to discuss before going into the design. For example, what do we mean by fusion zone? What do we mean by reinforcement? What do we mean by a throat? So as you people already know that a butt joint is uh, a, bu- a butt joint is a joint between two members like this, and in this I mean to say that in welding we provide weld here. In butt joint we weld here. So like this becomes member 1, this becomes member 2, and this becomes our weld. Okay, this is a basic design what we do in the butt weld. Regarding the same, we have one member here, we have one member here, and they are being joined by this weld, and welding has been poured on here. It has been done on here with the complete penetration, what we call actually as fusion zone, because this zone fuses the two members together, member 1 and member 2 together. So we call this as a fusion zone. So there are some technical terms that we need to discuss. First is the reinforcement. Okay, so what do I mean by the reinforcement? Reinforcement is actually this extra amount of weld that we give on both sides of the metal to make the throw dimensions at least 10% greater than the thickness of the welded material. Okay, this is known as, so for example, this is the actual thickness of the welded material, but we provide some extra 10% welding material here, 10% welding material here, so that the thickness of the total effective thickness of the weld is at least 20% greater than the thickness of member. Okay, TM, I'm writing it by this method. So let me write it for you. Reinforcement, I am writing reinforcement as RF. So it's the extra weld poured on a joint to make it 10% extra from the thickness of the welded member. Thickness of welded member. Okay. Then moving forward, so I will like to mention some more points in this. It is actually it is provided to increase the efficiency of the joint. Okay, increase efficiency of joint. Okay, That's why it is being provided there. Then we have what we mean by size of the weld. Okay, so next is size of the weld. Okay, size. So actually size of the weld is determined by the throat dimensions. Okay, this is called as the effective throat thickness. In case of complete penetration of a butt weld, the effective throat thickness is taken as the thickness of the thinner member. Okay, so for example, for this butt weld, we take the throat thickness as this. Okay, this is the actual throat thickness because here complete penetration has been taken. So throat thickness is taken as this, and this is also known taken as the size of the weld. So now we have some other specifications here. In case of full penetration, butt weld cannot be achieved. An effective throat thickness of 7 by 8, the thickness of the thinner member should be taken. Okay, and or if there is incomplete penetration, it is taken as 5 by 8 of the thickness of the thinner member. Okay, there are two cases for full penetration as per design. Okay, full penetration we are take it as 7 by 8 thickness of the thinner member. For example, this is the thickness. Since here both members are equal in thickness, so let us denote by that by t. If they were equal, then we have to take unequal, we have to take the thickness of the thinner member. For full penetration, we have to take the throat thickness as 7 by 8 of t, and for incomplete penetration we have to take 5 by 8 of thickness of the thinner member. Okay, so you remember this in case of butt welds. This is the size is actually I will write is, so size for butt weld, it is specified by the throat dimension. Okay, throat. Okay, it is specified by the throat dimension. And I told you for full penetration it is full penetration you have to take the size as 7 by 8 of t. For incomplete penetration you have to take it as 5 by 8 of t. Okay, then moving forward we have, okay, effective area. For this we have to see, so we were seeing all these things in actually butt weld. Let me take this as from here. Okay, so this is actually for hole for butt weld, that's why I'm putting it here. Okay, then we have effective area. So next is after size, first was size, next is effective area. Okay, effective area. Okay, so effective area is nothing for a butt weld, but it is the product of the effective throat thickness and the effective length of the butt weld. Okay, so it is product of, so it is actually the product of effective throat thickness and effective length of weld, length of butt weld. Okay, okay, this is there. And what we mean by this effective length, it is actually the length length of weld for which welding is done. Okay, done. So then we have to see its design procedure. Okay, design. What is design procedure for this? Mm, this no butt weld. We will see one more numerical example on this. Uh, for numerical example on this also, but we will first see the theory, then we will show numerical example on its design as well. So in case of complete penetration of the butt weld, the design calculations are not required, as the weld strength at the joint is equal to the strength of the member to be connected. So first point is, for complete penetration, design of weld, oh sorry, strength of weld, strength of weld is equal to strength of member connected. Strength of member connected. Okay, this is there. Now for incomplete penetration, we have to see how we have to design that. Okay, so for incomplete penetration, the butt weld, the effective throat thickness is computed and the required effective length is determined to furnish the strength equal to the strength of the members to be connected. Okay, so if I see in second case for incomplete penetration, what I calculate is, I calculate two things. Okay, effective throat thickness, TT, throat thickness I denote by TT, and I compute effective length, effective EL. Okay, I compute these two in such a way that is the total strength of the welded joint at the end will come equal to the strength of the members to be connected. Okay, so if I take P to be the strength of weld, okay, and sigma D is the permissible stress, either in tension or compression. Okay, and L is the effective length, I already told you effective length, and T is the effective throat thickness, okay. So then the strength of the weld is given by P to be equal to area of the weld, that is L times T times the stress sigma D. So from this equation I can compute anything. So for example, P is known. Okay, because I will be already told to transmit this amount of load, so this will be known either from throat thickness or the length of weld. I will assume one thing. Let me assume length of weld. Sigma D permissible stress is taken from the code, so easily I can get T, effective throat thickness, P divided by LD, L sigma D, all things are known. So by this method I can design my weld. Okay, so I hope this is clear to you guys up to this point. Okay, now the second part is design of fillet weld. Okay, design of fillet weld. So like in the design of the butt weld, I told you the different specifications. Similarly, in design of fillet weld, we have different specifications. We have to, or different technical terms, we have to learn about them. Then we can go on and proceed with the design of fillet weld. Okay. Okay, design of fillet weld. So the fillet weld is done for the members which overlap. Exactly, I told you, if the members are placed end to end like this, the members are placed end to end like this, we give the butt joint. Okay, but if the members are overlapping each other, so for example we have two members, I will show you clearly by the diagrams. We have one member like his. Okay, this is one member. Okay, sorry, I will make it like this. So we are having this one member. Okay, okay, this is one member. So I am not drawing this from this side because this is continuous from this side. Okay, I hope this is clear. So it is being overlapped on another member like this. Okay, there is a overlap like this, and this is also connected from this side. Okay, so I can make this. So there is a same, there is weld being put here. Okay, so for me this is member one. So this is member one, M1. This is M2. These are overlapping members, and I am putting this as fillet weld. Okay, so I hope it is clear for you. Well, fillet weld is for such joints where the two members overlap each other. And for this type of joint, neither tension nor compression is of any concern. The only stress that is of concern is the shear stress only. Okay, in flat weld, shear stress is important. Okay, in but weld, compression and tension were major members, but in flat weld shear stress is major member. Okay, so we have to design flat weld for shear stress importantly. Okay, that is important. So for this, we also have the same technical terms. First is the size of the fillet weld. So size of the fillet weld we assume as, for example, I told you here there are two members M1 and M2 overlapping each other, and a fillet weld of like this has been put here. So what we told as the size of the fillet weld is, first we will try to inscribe a largest right angle triangle within our weld. Okay, so what I mean by the largest inscribed right angle triangle, that is the corners of that triangle should touch the extreme our fillet weld or the cross section of the fillet weld at three different points. Okay, for that right angle triangle, if I see the largest length of the right angle triangle, that will give me the size of the fillet weld. Okay, so I define the size of the fillet weld as, the size of the fillet weld may be defined as the minimum length of the weld. The length is distance from the root to the toe of the fillet weld. That's why the one vertices of this right angle triangle is at the root of the weld, and another is at the toe. So the length of this leg is known as the size of the fillet weld. Okay, so it comes there size. So how we decide that? Either by inscribing a right angular triangle with equal sizes, or isosceles right angular triangle within there. Okay, I have shown those things in figures here. Okay, so first specification is size. Then we have uh, So this right angle equal side the right angle triangle is for that where the size of the legs is equal. But there are certain cases where the size of the legs may not be equal. Like here, for example, I have a beam flange here. It's a beam flange here to which a channel section has to be added here for fastener or something, for connector or shear connector or something. If I put flat weld here, I cannot increase the vertical thickness indefinitely here. Vertical thickness has to be equal to the thickness of the flange of this channel section. Okay, so there is unequal length of the legs of the flat weld. So I inscribe a isosceles inscribe a right angle triangle there and see what is the minimum length of the one side. That will be the size of this flat weld. Okay, for this is unequal legged flat weld. Okay, so this is important for you. I will write these two definitions here. Okay, size is given as minimum minimum length of the leg of weld, and leg we define distance between the root and toe of the weld. This is the definition of the leg. Okay, uh, so code has given us one more thing here. So he has given us what should be the minimum size of the weld. We denote size of the weld by capital letter S. Okay, what should be the minimum size of the size of the weld? It depends upon the thickness of the members that are to be welded using fillet weld. Okay, thickness of the thicker member, it's important here. Keep in mind thickness of the thicker member we have to take. In butt weld we have to take thickness of the thinner member. So if the thickness of the thicker member is up to 10 mm, minimum size of the weld should be 3 mm. Okay, it's accordingly 10 to 20 mm it is 5 mm, 6 mm, 8 mm, and 10 mm accordingly. So size we have to take it from the code. Okay, then we have one more definition is effective throat thickness. Okay, so as I told you, the definition of the throat thickness in butt weld, it is completely different definition of throat thickness in a flat weld. So throat thickness is the shortest distance from the root of the flat weld to the face of the diametric weld. Okay, joining the toes. So for example, I will have a weld like this. This is the cross section of the flat weld. Okay, remember. So these are its toes. T T. This is root R. So if I inscribe a right angle triangle into it like this length I call as the distance between the from the root to the opposite diametrically. This is along the diameter, no? Diametrically another side that is joining the two toes. Okay, so I call this as effective throat thickness. Okay, and this is actually has to be the shortest distance. Okay, we could have taken the throat thickness to be this also, but out of all these you will see this to be the shortest distance. So we take it as effective throat thickness. Okay, shortest distance, short distance between root and diametrically opposite weld face. Okay, what is the opposite weld face of that lies in the diametrical direction? We call the distance between the root and their side to be the effective throat thickness. Okay, so this is third, I guess. Okay, and we take as effective throat thickness. Okay, ETT. Okay, ETT, effective throat thickness, to be equal to some constant K times the size of the weld. Okay, remember K times the size of, where the value of the K is a constant, and K depends upon the angle between the fusion faces. Okay, so these are the fusion faces actually. So we have one member like this to be joined and another member like this to be joined. So whatever will be the angle, if this is alpha, so whatever will be the angle of these two faces to be joined, we call it as angle of fusion. So it depends upon the angle of fusion. So as per the code here, we have a table. So angle between the faces, if it is between 16 to 90 degree, we take the value of K to be 7.7, 0.6, 0.65, 0.6, 0.55, and zero point 0.5. Okay, effective throat thickness accordingly. Then we have effective length of the weld. Okay, here we have effective length of the weld. Effective length of weld. Okay, and remember, this is we are talking all story about fillet weld. For butt weld, I already told you all the things. So effective length, if I have to define, I will define it as the length of the weld, fillet weld, for which the specified size and throat thickness of the weld exists. Okay, so for whatever length, the specified throat thickness and the size of the weld exists, that is known as effective length of the weld. So for example, if this has to be, for example, if this has to be the size of the weld. Okay, okay, this has to be the size of the weld. Okay, this has to be S, and this has to be S, and this is the another diametrically opposite face weld face. Okay, so and this is the throat thickness KS. You already know, I already showed you KS. So if this is existing over the following length, so if this is continuing along this length, this is continuing along this length, throat thickness and the effective throat thickness as well as the size of the weld is continuing up to some distance like this, and there we have again, we again have these things there. Okay, so up to this point, if they exist, so I hope you are getting a clear message from this. You are getting what I want to try to make you understand. So whatever is the length between these two sections, this length is known as effective length of weld. Okay, EL I will represent. So it is actually the length of the weld for which the size of the weld as well as effective throat thickness exists. That is known as the length of the weld. Okay, so uh, we take this as overall length minus twice the weld size. Okay, deduction is made to allow for the craters to be formed at the ends of the welding length. So if L is the total length of the weld, we take effective length as L, effective length EL to be length of the weld minus 2 times the size of the weld. Okay, that is there. I will write the definition for you. It is length of weld for which effective throat thickness EFTT and size exist. Okay, it is equal to overall length overall length of weld minus twice the size of the weld. So this is being given to minus twice the size of the weld to provide provision for craters. Craters are some, like I mean to say that some voids, because at the end of the weld some voids are being created or some gaps are being created. We provide so to include those provisions as well, we deduct twice the size of the weld to provide a provision for the craters at ends. Okay. So like here, this is the effective length of the weld. Okay, here we have to do it like this. There are more important things in this effective length, but I hope for this course you have to understand up to this point. Okay, then moving forward, we have the effective area of the weld. Okay, what I mean by the effective area, same like whatever I mentioned you in the butt joint, it is the same. Effective area of a fillet weld is equal to the effective length of the weld multiplied by the effective throat thickness. So here it is important to note that, so in butt weld, if we were having butt weld like this, so we took this as effective area. Okay, but here the effective, because there the weld was in tension and compression, so the area that was coming into picture was a cross sectional area. Same, you might be having same intuition here also, like why we are not taking the cross sectional area of the butt weld, but here I already told you that cross sectional area of the flat weld, here I already told you that flat weld is in flat weld the predominant stress is shear stress, so we have to take the shearing area here. Okay, so effective area, okay, effective area of the flat weld. So if this is the total weld. Okay, okay, this is the right angled triangle at one side, cross section, this is actually the cross section. Okay, so this is the weld, whole flat weld that is being made. And could you please mute your mic and switch off the camera? So this is for example, this is your fillet weld. I am showing you the 3D picture of the weld. You won't see any types of these diagrams on any books. It is to make you better understand what actually this concept is. Okay, so this is the length of the weld. So here the shearing area, I want to mention you here what I mean by shearing area. So shearing area is actually this. Shearing area is this. Okay, so for the calculation of the effective stresses on this flat weld, you have to take the shearing area, not the cross sectional area. Okay, cross sectional area we will taking in butt joint. Okay, butt weld, sorry. So this was the cross sectional area. This we are not taking this, but we are taking the shearing area. So this is the size of the weld here, SS, this is SS, and this is the length of the weld, and this is throat thickness, you already knew that this is K times S. So we take the effective area as product of effective length. So this is effective length and size of weld. Okay, so effective area is equal to the effective length of the weld multiplied by the effective throat thickness. Okay, that is there. Product of effective length and effective throat thickness. I hope this is clear to you. So then we have design. How we design this fillet weld. Okay. Design of fillet weld. Design of fillet weld. Okay. Please keep your attention here because this is the important thing. After all this, we have to solve the numericals on this also. So the following assumptions are made while the analysis of the welded joints, which are fillet weld in nature. So the first assumption that we made in the analysis is this welding material or the parts that are being connected are homogeneous, isotropic, and elastic elements. Okay, this is important. Homogeneous, isotropic, both the weld material as the members to be connected, and elastic materials. Okay, and second important assumption is whatever the parts are to be connected, they should be rigid. Parts should be rigid so that deformations there in other deformations are neglected. Okay, this is important. And third assumption is that uh, external stresses what I mean by external stresses is the stresses induced by the external joints only, external loads only, though those only have to be taken in consideration. Internal stresses and residual stresses are to be ignored in the analysis. Okay, so then we have the design procedure. So for the design procedure, for first and the foremost thing that we do is we assume the size of the weld. Okay, and first thing is assume size of weld. Okay, assume size of weld s. Okay, mm. Then from that size of the weld we calculate the effective throat thickness. Effective throat thickness, EETT, is equal to K times the S, where K is the constant whose value depends upon the angle of the fusion between two members to be connected by the fillet weld. You have to take this value from the code. Okay, so it's from code. So we calculate effective throat thickness T, and let L be the length of effective length of weld. Effective length. So effective area becomes T times L. I already told you it is the product of the effective throat thickness and effective length, and T is internally equal to K times S. That effective area becomes K times S times L. So the force that it will transmit, or the load that it will transmit, is equal to the allowable stress times the effective area. So that is K times S times L times allowable shear stress. I told you why we are taking shear stress here in fillet weld only, because the fillet weld is designed is is such a type of weld that is predominant in shear only. Butt weld is predominant in tension and compression. So we have to take the allowable shear stress of weld in Newton per mm square or megapascals. Okay. So then the strength of the weld P we calculate as KST times T tau VF. Okay. This is the formula, and this formula you have to use in the design procedure also. Okay. So after this, what we can do from this formula is that pull or the thrust to be transmitted by the connections is estimated. We can estimate that from this, or we know that pull or the thrust that has to be transmitted by the members P is known. Okay, we can divide P divide by K S T tau VF. We can calculate the effective length of the fillet weld. Okay, effective length we can calculate. Okay, that thing is there. Okay, or if only longitudinal fillet weld is made, a check is provided to see that the length of each longitudinal fillet weld is more than the particular perpendicular distance between them. It is important. Okay. And returns of the length twice the size of the weld are provided at each end of the longitudinal fillet weld. Okay. These things have to be mentioned. So when we provide weld here, like for example, we provided weld here, we have to provide end returns here like this, and end returns here like this. These are equal to twice the size of the weld, twice the size of the weld. I told you why we are providing this, to give the provision for formation of the craters. Okay. Then moving forward, we can go directly to our design problems. Okay. Let us start with this problem first. So our example problem first is two plates of thickness 16 mm and 14 mm are to be joined by a butt weld. Okay. In the figure you can see two plates as figure. The joint is subjected to a tensile force of 218 kilonewton, 280 kilonewton. Okay. Due to some reasons, the effective length of the weld that could be provided was 175 mm only. So the effective length provided is 175 only because of some fabrication process or fabrication constraints. Okay. We have to check the safety of this joint. Okay. We have to check whether it will transmit 280 kilonewton safely or not. So how we can check is we have to calculate the strength of this butt joint, butt weld, and we have to check if that strength is greater than the load to be transferred, then the joint is safe, or if it is less, then it is inadequate. Okay, let's begin. So here it is single V butt weld is provided and double V butt weld is provided. For your information, I want to mention that for single V butt weld there is incomplete penetration, and for double V butt weld there is complete penetration. So taking the first case, single V butt weld, okay, is provided. Okay, zero. First case is incomplete penetration. Okay, so for incomplete penetration, so I already told you, for incomplete penetration, if there is incomplete penetration, what you have to take the effective throat thickness. Effective throat thickness you have to take as 5 by 8 of thickness of thinner member. Okay. So out of these uh, thickness of the thinner members, okay, 14 mm is the lowest. So 5 by 8 of 14 comes out to be 8.75 mm. I have to take the effective throat thickness. Okay. And it is also provided, given that effective length of the weld is 175 mm. Okay, effective length already given 175 mm. Okay. So the strength of the weld, So the strength of the weld is effective area. Effective area is nothing but the multiplication of the effective length times the throat thickness. Okay, L times T times allowable stress. Okay, sigma D. Okay, so sigma D we have to take as 150. Okay, we have to take it from the code 150 megapascal. Okay, if we plug in all the values, 175 mm, T is 8.75 and sigma is 150. This comes out to be 229 kilonewton, which is less than 280 kilonewton to be transmitted. So this joint, that is single V joint, single V weld joint, is inadequate. Okay. So second is double V joint. Okay. Double V weld. Okay. So double V weld means complete penetration. Okay. So for complete penetration, effective throat thickness T has to be taken as 7/8 of, okay, sorry, for the complete penetration we have to take the effective throat thickness as thickness of the thinner member to be connected. Okay, thickness of member. Okay, that is equal to 14 mm. So if you calculate the strength, that comes out to be 367 kilonewton, 0.5 kilonewton, that is greater than 280 kilonewton. So this section is this weld is adequate. Okay. Okay, we solved the first problem. Then moving forward, we have one more problem. A butt weld is used to connect two plates, 180 mm and 18 mm each. Find out the stress developed in the weld if it's subjected to a moment of 1300 kilonewton meter. Okay, so the moment that it is subjected to, so moment that is subjected to is 1300 kilonewton mm. Okay, 13,000 kilonewton mm. Okay, so if we assume the butt weld to be U type. Okay, so this is the U type butt weld. Okay, so this is one member like this, this is another member like this to be joined by the butt weld, and we assume butt weld to be like this. Okay, not V, this is the weld provided there. Okay, and its length is like this from this side. This has to be 180 mm, and this is the 18 mm because 18 mm. If we take the section modulus of this section butt weld, okay, section modulus will be BD square by 6. So here B is 18 and this is D. Okay, B is 18 times 180 square divided by 6 section modulus Z. We represent it by Z. Section modulus of the butt weld. Okay, it comes out to be 97.2 10 to the power 3 millimeter cube. Okay, and for butt weld you have to take from the code permissible bending stress. Okay, code says that for a butt weld permissible bending stress is 165 newton per mm square. Okay, okay, So the stress that it is being able to resist sigma will be equal to section modulus z multiplied by, sorry, moment divided by the section modulus. Moment divided by the section modulus. Moment is 13,000. Section modulus is 97.2 into 10 power 3. Make sure you are consistent with the units, okay? So it comes out to be 133.74 megapascal, so which is less than 165, okay, megapascal. And hence the stress that is coming on our butt joint is less than the permissible stress, so it is safe, okay. Then we have one more problem is a tie member in a truss girder which is 250 mm by 300 mm in size is welded to a gusset plate of 10 mm thickness by a flat weld, okay. The overlap of the member is 300 mm, so there is a constraint on the overlap that it has to be 300 member only, 300 mm only. The weld is 6 mm in size, okay. Find the strength of the joint by welding is done if the welding is done is like this, okay. Welding is like done like this. So okay, with the increase in the strength, if the weld is done all around, okay, allowable shear stress we have to take is 180 newton per mm square, okay. Now let's begin this problem, okay. So the size of the weld, first we will calculate the effective length, okay. Effective length comes out to be, it will be equal to this length plus this length plus this length. Effective length will be 2 times 300, 2 times 300 plus 250, okay. This comes out to be 850 mm, okay. And effective throat thickness ETT of a flat weld is K times the size of the weld. Size is already given to be equal to 6 mm. So let us take K to be equal to 0.7 for angle of fusion 45 degree, S to be 6 mm. This comes out to be 4.2 mm, okay. So strength of flat weld, strength is allowable stress times effective area, that is ks times L. So it is 108. It is already told 108. You have to take allowable shear stress 108. So this is tau VF. Sorry, tau VF. Okay, 108 times 850 times 4.2. This comes out to be 385.56 kilonewton. Okay. So this is the, if the welding is done on only 3 faces. If the welding is done on all the 4 faces, so effective length comes out to be 2is 300 plus 250. That's the perimeter, okay? 2is length plus breadth. That comes out to be 1100 mm. So accordingly, the strength comes out to be, strength will be larger, and it comes out to be 498.96 kilonewton. Obviously this is larger, okay. Now the extra difference between 490 and 385 is we have an addition of 113.4 kilonewton. I hope you guys are following me, okay. These problems are very easy, and these are actually the design problems that you have to tackle, okay. There is one design problem, these were analysis problems. Now we will see one design problem and then we will close the session, okay. So a tie member 75 mm times 8 mm is to transmit 90 kilonewton load. So design a flat weld for this. For so let us and calculate the necessary overlap. So let us quickly solve this design problem. Okay. So this is a flat weld. So flat weld is, so strength of weld should be, strength of weld should be equal to load. Okay. For safe, that should be 90 kilonewton. It is there. minimum. So 8 is the thickness of the thinner member. So as per ICE provisions, minimum size, minimum size, minimum S for 8 thickness of the member, it has to be 3 okay. And maximum size, as per IS, it has to be 8 minus 1.5, that is the thickness of the thinner member minus 1.5, it has to be 6.5. So size of the weld should be between 3 to 6.5 So let us assume a size of 5 okay. Let's assume this size of 5 and let's assume K constant to be equal to 7. For an angle of fusion to be equal to 45 degree, we are assuming K to be equal to 0.7. Okay, assume. So effective throat thickness T comes out to be Ks. It comes out to be 0.7 times 5 is equal to 3.5 Okay. So effective length of the weld. So the strength of the weld P is actually equal to tau VF times uh, effective throat thickness T times the effective length of the weld. So effective length of the weld I will write is LE is equal to P times tau VF times T. So from this we will get the effective thickness times allowable stress. So strength is 90. So we have to divide by effective throat thickness is 3.5 and allowable stress is 108. So effective length we have to provide to be 240 at least. We have to provide 240 So if we weld the gusset plate on both the sides, like on both the sides, like this side and this side, we will be able to provide this 240 okay. So length on each side is equal to 240 divided by 2, which is equal to 120 and which is importantly not less than 75 okay, because this perpendicular distance between two fillet welders should be greater than should be less than the I mean say that the effective length of the two weld single weld should be greater than the perpendicular distance between the two fillet welds. I already told you this in the specifications. Okay, then if you want to add the weld from this, overlap will become minimum. So it was 120 earlier. If you add the weld on this side also, overlap will become 85 accordingly. And accordingly, if you provide on all the four sides, overlap will become minimum to 45 So you have to solve this problem like this. Then I have given some more problems like this 3.5 here, this and 3.6. I want this you to try at your place and see if you will be able to solve this. This is homework. So thank you everyone for joining. If you guys have any questions, you can ask. If you don't have any questions, then you can disperse. I,
Hello, sir.
yeah, you can ask.
Yes, sir. Sir, if the fusion angle is given a certain range, so like around 60
Okay,
to
like
120.
1 second, I will take that slide. Yeah, here.
Like if
Okay,
if it is like more less than 60 or greater than 120,
okay.
so what we should consider for the k value?
I don't think if those angles are not covered by the code, no, then the
Huh.
problems will not be for those fusion angles because the code has
Okay.
strictly specified the angles of the fusion. Other because those flat joints would not be adequate or those not will be safe for the construction. That's why those angles are not provided. That's less than 60 or greater than 120. I hope you got the point.
Yes.
Yeah,
And
that's why
also,
those
yes, sir.
fusion angles not recommended by the code.
Mm-hmm. Also, the last sentence when you are saying about the length of the effect, total length of the weld,
Hmm.
the perpendicular length and the parallel to the length. I mean,
Yeah,
last
yeah,
by
yeah,
last problem. That
yeah, yeah.
can you repeat that again, sir?
Yeah, sure. So you saw that the total length for the well to be provided was 240 mm. Is it okay to you?
Yes.
240 mm. Then I told you first I will try first trial where I will take the welds on both sides of the cassette plate here. Okay.
Hmm.
So it will be, if I divide 240 into two halves, I will get 120 mm.
Yes.
So for one individual weld on the one side, the length has to be 120 mm at least. Okay.
Okay.
And overlap has to be 120 mm. That is, this member should be at least 120 mm on the gusset plate. Okay.
Huh.
Is
Okay.
it okay? And we have a dimension of the tie member also. That is, it is 75 mm in breadth and 8 mm in thickness. So we can see that the distance between the two welds that are parallel to each other, perpendicular distance between them is 75 mm. Okay.
Hmm.
And that 75 mm is less than their individual length, 120 mm.
Okay.
So it is important in the design specifications that uh, if two welds are parallel to each other, the length of the individual weld should be greater than the perpendicular distance between the welds. Okay.
Yes, that particular sentence, sir. I can you. I mean, I was not able to catch that one.
Yeah, you got that now.
No, sir. Can you repeat that again?
The length, if the two welds are parallel to each other, these two welds are parallel to each other.
Okay.
Okay. The length of the individual weld, the length of
Okay.
the individual weld
Individual. Hmm.
should be greater than the perpendicular distance between the two welds.
Okay. Acha. Mm-hmm.
120 is
Got it.
greater than 75.
Yes.
Yeah, that then this design is okay.
Acha.
Yeah.
Got it. Thank you.
Anything else?
Nothing else.
Okay. Okay, thank you for joining the session.